Today I am going to discuss about heat transfer. So basically, I am going to cover this topic is conduction, Fourier's law of heat conduction, parallel and series conduction of heat transfer, thermal conductivity of a constant thermal conductivity, and rate of heat transfer. So all these topics will be covered here. So I will go one by one. Okay. So first of all, what do you mean by heat transfer? So basically, you know that any object has a high degree of temperature. For example, it has a temperature of approximately is equal to 200 degrees Celsius, and another object is there. It has having a temperature of 150 degrees Celsius. So there is a difference in a temperature, and when there is a difference in a temperature, so what will happen? So definitely there will be a flow of heat, and this flow of heat is known as heat transfer. So heat is the form of energy which transfer from a body at a high temperature to a body at a low temperature. Okay, so it is the form of energy, and we can say that there is a flow form. Okay, this is your flow form of energy, flow form of energy. We cannot say that an object is having it has a heat. It has a heat. We can't say that. Heat is a transient phenomena. Whenever there is a temperature difference, then heat comes to the play. Otherwise, heat is not in on the content. If you will tell about that any object is having a heat content on it, so it is wrong to say. It is wrong to say that any body has a heat content. So we need to understand that heat is the flow phenomena. Heat is a flow phenomena or transient phenomena. So heat will always transfer from high temperature to low temperature, and this will happen. Okay, so this is the basic definition of heat transfer. Heat transfer, there are three modes of heat transfer. There is conduction, convection, radiation. So one by one I will discuss each and every modes of a heat transfer. Okay, so first of all, what is conduction? So the process in which heat transfer from one part of the body to the another part, from particle to particle, in the direction of the fall of a temperature without actual movement of heat particles. Let us consider there are so many particles are there. So all are arranged in a form of solid. So what happened? There is a transfer of energy. In this type of things, there is a transfer of energy. So let us suppose this has energy E. It has an energy. So what happened? Beside this molecules or atom, it has low energy and it has high energy. So it will transfer its energy to this molecules. Again, it will transfer to this molecule. So without any movement of the molecule itself, there is a transfer of heat, and this type of heat is known as this type of transfer of heat is known as conduction. Okay, so this is the conduction. So from figure you can understand that there is a heat in one part, and if you saw that the temperature is rising. Okay, so heat is going to be conducted. Okay, and heat will always flow from high temperature to low temperature. So this part is your high temperature, and this part is a low temperature at all. Now I am going to discuss about Fourier's law. What is Fourier's law? So it will basically give you the context of how heat is being transferred as per the Fourier's law. So let us consider here, this is a metal, and what happens, heat is being supplied to this metal. So what will happen, molecules start gaining energy. So atoms are energized and vibration increases, and due to its vibration, what will happen, it will transfer its vibration form of energy to the local one, and this will help to the conduct the heat energy from one part to another. So in this way, both the sides heat will be transferred. So in Fourier's law, what happens? Fourier's law, as per the Fourier's law, what happens? Heat transfer rate will be equal at any place. This is very important. As per the Fourier law, will be heat transfer rate will be same, will be constant for overall overall body. So here what we see here is we see that there is a high temperature. We can consider one wall of the body has a high temperature, and another body has a low temperature. So what will happen? Heat will transfer from high temperature to low temperature. And let us consider there is a body's thickness, that is del x is your thickness, or we can also consider as L. So as per the Fourier's law, what happens? Rate of heat transfer, that is Q dot, is proportional to area. The more is the area, the more heat rate of heat transfer is there, as well as change in it is directly proportional to the difference in the temperature. Suppose there is a more difference, so there will be more height rate heat of transfer is there. Okay, if there is a less temperature difference, so it will transfer heat slowly. Again, it is inversely proportional to the distance. Let us consider there is a high temperature the left side and there is a low temperature right side. Right side there is a low temperature. So the gap between these two, high temperature and low temperature, will be high. Then rate of heat transfer will be reduced. And if gap is less, then it means that rate of heat transfer will be high. So it is inversely proportional. So we can write here like this. So finally, what will happen if we will remove all the constants? So what will happen? So this is your proportionality constant. So by removing proportionality constant, we will get the equation like this. So this is the Q conduction. That is equal to Q conduction is equal to minus Ka dt by dx. I hope you have understood now. Okay. Again, in the better way, if you want to understand, so let us again show you once again. As per the Fourier's law, it has been seen experimentally that heat transfer rate is directly proportional to the area of section as per perpendicular to the direction of heat flow. So this area. So let us consider an object here, an object. Okay, and an object is in the form of 3 dimension. So this is at a high temperature and this side it is your low temperature. So the area of cross section, I am talking about the area of the cross section. I am talking about the area of cross section. These are the area of cross section. So this area, if it is your more area, so more heat transfer take place, and if the area is less, so less heat transfer take place. So finally, heat transfer, that is dq by dt, is directly proportional to the area of cross section. So this is the equation number 1. So we can consider this. Now it is directly proportional to the temperature difference between the two phases. The more is the difference in the temperature. If there is a more difference in a temperature, so this is a high temperature and this is a low temperature. If there is a very large temperature difference, then what will happen? There will be more high rate of heat transfer will happen. So from here we can understood that that is a rate of q dot, that is dq by dt, that is rate of heat transfer, is directly proportional to the difference in a temperature. So this is very simple equation. I hope you have understood now. Now what is temperature difference? That is equal to high temperature minus low temperature. So this is, you need to understand this that rate of change in a temperature can be written as high temperature minus low temperature. Now it is also inversely proportional to the thickness of the slab. So let us consider there is a thickness of slab is T, or thickness of slab is L. So it is inversely proportional. So finally we have got the equation third equation. Okay, Q dot, and that is equal to dq by dt is inversely proportional to 1 by x. So how many equations we have got? If I will go back side, so we will get one equation, dq by dt is proportional to a. So here we are getting dq by dt is directly proportional to a. So this is equation number 1. dq by dt is directly proportional to the temperature difference. This is equation number 2. And dq by dt is inversely proportional to 1 by x. So these are the equation third. So if we combine 1, 2 and 3, so what we are going to get? So we are going to get dq by dt is proportional to area into change in temperature divided by dx. So finally we are getting if you remove the constant of proportionality, so what we will get? So dq by dt is equal to K dt Ka dt by dx. So I am just considering dt by dx. So I am just considering change in temperature is small and change in length is small. So finally we are getting a k is a constant form. So if you get k as a constant form, so k is known as constant of proportionality, and it is also called as thermal conductivity of a material. And dt we have understood that it is a change in temperature, and dx is the length change within the above parameter. What do you mean by above parameter? Let us consider there is a high temperature and there is a low temperature. So I am talking about the change in the length. Okay, as we go from high temperature to low temperature, there is a change in a length. If we go more lower temperature, so change in length will increase definitely. So definitely we are talking about this is a change in a length. So finally we have got one equation, and this equation is also known as Fourier's equation. This is a very important equation to be used everywhere while doing a numerical. So this is known as Fourier's equation, Fourier's law, Fourier's law. So I hope you have understood this Fourier's law of, and Fourier's law have given this equation. Okay. Here I am using a use case experiment, a practical experiment, that how to use the Fourier's law. So let us see here how to use all the Fourier's law. Let us consider this is a body, and it has an area of cross section A as a uniform cross section area, and this body has a width or length, we can say it has a length L. Okay, and it has a temperature T1 and T2, and one side temperature, it is a high temperature, and T2 is low temperature. So when T1 is equal to high temperature and T2 is equal to low temperature, and the thickness of a slab is L, and area of top cross section is A. So here what we have studied, as per the Fourier's law, Q dot is equal to minus Ka dt by dx. Why I have put the negative sign? Because heat transfer rate will decrease as the distance increases. So it is decreasing, heat transfer rate will decrease. So here Q dot is equal to minus Ka dt. What do you mean by dt? Dt means change in temperature. So how much change in temperature is? It is the final temperature minus initial temperature, that is T2 minus T1, divided by change in length. Dx means change in length. So if I, in place of dx, we can write here L, because total change in length L, length from x is equal to 0 to x equal to L. So finally change in length, that is del x, can be written as L minus 0, that is equal to L. Now we know that T2 will be always a lower temperature and T1 will be high temperature. Okay, so what will happen here? If I will put K A T2 minus T1 divided by L, so as we know that these terms will be negative, because T2 is lower temperature and T1 is a high temperature. So, and already there is a more negative. So finally, if we reverse this, then negative will get cancelled out. Negative will get cancelled out. So finally, we can write here Ka into T1 minus T2. So finally, we have got Q dot is equal to Ka by L into T1 by minus T2. That is high temperature or minus low temperature. T1 is a high temperature, so we can write high temperature minus lower temperature. That is temperature difference in a positive form into Ka divided by L. So this is very important formula for solving any type of numericals. Okay. Now one more thing we need to understand here. One more form we need to understand here. Let us consider here Q dot is equal to Ka T1 minus T2 divided by L. Now, if I have taken T1 by T minus T2 divided by, just we have reversed L by divided by Ka. So here we can write Q dot as a heat flow. So can we tell here that T1 minus T2 is what? Temperature difference. And we need to compare this. What type of comparison we need to understand? We know that current, if we if we compare heat flow as a current flow to heat flow, then what we will get? Heat flow. So current is I, heat flow, and heat flow, this is a Q dot. If current is potential difference, there is a potential difference. So here it is your temperature difference. So temperature difference, there will be temperature difference, that is del T. So these are the analogy we can use this. So in current, there is a resistance. So in place of resistance, we can see that, see here, Q dot is what? As we use this analogy, I is equal to V by R. Again, we see that I, in place of I, this is a Q dot. In place of a T1 minus T2 is a V. Then whatever it is left, it is the resistance. So in place of resistance, we can say that it is a thermal resistance. So finally, we can come to the conclusion that thermal resistance is can be written is by L by Ka. So this is very important derivation. So finally, we have got the formula Q dot is equal to change in temperature divided by thermal resistance. So this is very important. Okay, where RTS is equal to length by K into A, where L is the length or thickness of the slab, K is the thermal conductivity, and A is the area of that slab. So I hope you have understood now. Now, why we have taken this analogy? So that we can solve most complicated questions, and we can solve most complicated equations and most complicated problems. So if there are so many, let us consider here, if there are so many numbers of layers of a slab with different properties, then in that case we need to solve it by analogy of resistance. Let us consider, we have already discussed only for a two term. Okay, that is, one is high temperature and one is low temperature, and the material having a thermal conductivity K. But now we need to understand that if there are multiple number of metals or multiple number of material having a K1 as a thermal conductivity, another has a K2 thermal conductivity, another part it has a K3 thermal conductivity, another part it has K4 thermal conductivity. Then in this case how you will able to find the rate of heat transfer? So if we want to find the rate of heat transfer, then use the formula analogy of the electrical resistance. So if we use the analogy of electrical resistance, so how you will use this? So let us consider this is a Q dot, and Q dot is equal to Q dot, that is rate of heat transfer, is equal to del T by RTH. What is RTH? So RTH is total thermal resistance. Total thermal resistance. So if there are ample or multiple number of material, then we need to solve the total thermal resistance of this whole body, and after that we have to find the change in temperature, that is high temperature minus low temperature. Now here total resistance can be found by analogous to the electrical circuit. So how we will make the electrical circuits? Let us see here. See, this K1 and K2 both are in a series. So can we write here is as a R1 and R2. Now K3 and K4 both are in a parallel. See, these are in a series. These are in a series. But as soon as we go for a third part, so it is a parallel. Okay, so it is a parallel. So we have got how many resistance? R1, R2, R3 and R4. So we can easily find R1 as R1 is equal to how much? Because we have known that R is equal to length L by Ka. So R1 can be written as L1 by K1A, K1A, A1, and R2 can be written as L2 by K2A2. R3 can be written as L3 by K3A3, where L1 is the length of this part, L2 is the length of this part, L3 is the length of this part, L3 is the length of this part, sorry, and L4 is the length of this part. So by using this, you know the area, suppose it has area A1, it has area A2, it has area A3, it has area A4. So different area, you may get different area. Finally you have got all the resistance. As soon as you have got all the resistance, so what you will do? You will need to understand that we have to use the electrical analogy. So as we know that these both R3 and R4 are parallel, so by using R equivalent is equal to 1 by R3 plus 1 by R4, so we will get R equivalent plus. So in place of this, what we will get, see here, in place of this we have to use like this, R1 plus R2 plus R equivalent dash. So finally, or R1, R2 and R equivalent dash we have got, because by using this equation we will get R equivalent. So finally we will use this. You have you know about the electrical circuit, how to find the resistance of the electrical circuit. So by using this only you will able to understand that how we can implement this. So finally you have got total thermal resistance. Suppose you have got total thermal resistance as RTH, total thermal resistance as RTH, total RTH equivalent. Then by using the formula Q dot is equal to change in temperature difference by change in temperature difference by RTH equivalent. So change in temperature difference, you should take, always take TH minus TL. You can also take mid temperature as well as. But if you have you are having a first and last option, that is high temperature and low temperature at one end. So by using this we can solve this. Okay. So this is the way by which we can solve the heat transfer rate. We can find heat transfer rate. Let us do one of the examples so that you will able to understand how to solve this type of problem. So in the problem, we need to understand what question they are asking. An iron bar of length L1, that is equal to L1, we are having L1 is how much? 0.1 meter, A1 0.02 meter square, K1 79 watt, and brass of length L2, see here, this is your iron bar, so it has L1 and brass L2. Okay, and the area is A1 is how much? A1 is 0.02 meter square, and brass is having a same area, that is 0.02 meter square. Okay, we have got, as well as we have also got thermal conductivity. From here we can see the thermal conductivity. Let us see here. See, let us again see here. Length, they have given length L1 as 0.1 meter. So that is L1, we are having L1 is equal to 0.1 meter. A1 is how much? A1 is 0.02 meter, 02 meter square. So this is a 0.02 meter square. If I am talking about K1, so K1 we are having a K1 is equal to 79 watt per meter Kelvin. So we have got this. Now again, if we talk about L2, that is L2 is the brass. So brass is having a length of L2, that is L2 is equal to 0.1 meter, and A2 is same, that is equal to 0.02 meter square, and the K2, that is thermal conductivity, is how much? Thermal conductivity is 109 watt per meter Kelvin. Okay, so finally we have got all the things, okay, are soldered end to end as shown in a figure. The free yield of the iron and a brass bar are maintained at 373 and 273. So if I am talking about temperature T1, that is high temperature is 373 and low temperature as a 273 respectively. Obtain the expression and hence compute the temperature of the junction of the two bar. So as we know that heat transfer rate will be constant everywhere. As we know that heat transfer rate is constant. So if heat transfer rate is constant, that is heat transfer at this point everywhere will be same. If we talk about heat transfer rate, that is Q dot at this point, at this point, at this point will be same. So finally, let us consider at this point the midpoint between the temperature between midpoint will be T naught. Okay. So by using this concept, by using this concept, we should use this concept to find out the expression. So how you will find? So let us see here, heat transfer rate in the iron bar. So let us consider this is an iron bar and it has temperature T1 as T373, and it has at the end it has a T0 as a temperature, but we don't know the T0. But if we talk about heat transfer rate, that is Q is equal to Ka. So K1A1 high temperature, that is 373 minus T0 divided by length, and length is how much? Length is 0.1 meter. Okay, so that is L1. We can, as we have studied all the things, what are the formula, we can use this. Okay, so let us solve one question, very important question, so that we will you will able to understand the concept. So before that, we need to understand what the questions are asking. And an iron bar of length 0.1 meter. So let us consider this is an iron bar having a length is how much? 0.1 meter, and the area of cross section is 0.02. So we can write here area, that is A1 A1 is how much? A1 is 0.02 meter square. Now again, this is length L2. L2 is 0.1 meter. It is given L2 is 0.1 meter, and if we consider A2, so it is 0.02 meter square. And what about K1? So K1, this is the thermal conductivity of the iron. So this is K1 is 79, and K2 is K2 is 10. Here we can see that it is 109 watt, 109 watt per meter Kelvin. So we have got this. Okay, so we need to find this temperature T naught. Okay, so the three ends of the iron bars are maintained at a temperature of 370 and 273. See here, temperature has been maintained as 373 as well as 273. Obtain an expression for and hence compute the temperature at the junction of two bar. So we need to understand that what is the temperature at T naught. As we know that, as we know that rate of heat transfer will be uniform throughout the body. Rate of heat transfer, that is Q dot, will be constant throughout the body. Throughout the body. So if this is the concept, so if we talk about Q dot, so Q dot can be written as K1A1 by L1 into T1 minus T naught. We can also write this Q naught as K2A2 by L2 is equal to T naught minus T1 T2, because it is a high temperature. If we talk about T naught for the case of brass, T naught is the high temperature and T2 is the lower temperature, right? That is 273. So by using this equation, we can put the values. So that is, if we know that equation, we have derived the expression. Again, I am writing expression, that is K1 A1 by L1 into T1 minus T naught, and this is equal to K2 A2 by L2 into T naught minus T2. So as we know that from here, from the data, if we saw the data, length of the both the L1 and L2 is are same, area and A2 A1 and A2s are same. So if we know this L1 and L2 are same, so we can cut this, and area is also same, so we can cut this. After cutting this, we need to put the values. So if we want to put the value in place of K1, it is 79, and 79 T1 is 373 minus T naught, and this is equal to K2. K2 is 109 into T naught minus 273. So finally, we can write here 79 into 373 minus 79 T naught. This is equal to uh, this is equal to here, 79 into 373 minus 79 T naught is equal to 109 T naught minus 273 into 109. So finally, if we rearrange this equation, so we will get 109 T naught plus 79 T naught is equal to 79 into 373 plus 273 into 109. So finally if we add this, so how much I'm getting here? 998 188 188 T naught is equal to 79 into 373 plus 273 into 109. So finally T naught, if we divide it to all the equations, so we will get 315 Kelvin approx. So this is the solution of this equation. So I hope you have understood this. Okay. Now the second part, if I'm talking about a second part, so what is second part? In second part, they are asking equivalent K equivalent thermal conductivity, equivalent thermal conductivity. Okay. So if equivalent conductivity is so K equivalent. So as we know that the resistance is thermal resistance RTH is equal to L by Ka. So K is inversely proportional to the resistance. So if resistance are in series, see we have already seen that this is a iron bar and this is a brass. All are both are in series. So we have to add R1 plus R2, but we need K equivalent. So if you want K equivalent, so it is inversely proportional. So 1 by K equivalent will be equal to 1 by K1 plus 1 by K2. So by using this equation, so we can use 1 by 79 plus 1 by 109. 1 by 109. So finally, K equivalent will be K equivalent if we calculate this. So finally, K equivalent will be 91.6 watt per meter Kelvin. I hope you have understood this. Now, the heat current through the compound bar. So what is heat current? So how you will define heat current? Heat current. We need to find heat current. Okay. So heat current, basically they are asking about heat transfer rate. So before that we need to understand, we need to keep here K equivalent of the both the bar is equal to 91.6 watt per meter Kelvin. So basically we need to find now heat transfer rate. So how you will find heat transfer rate? That is Q dot. Q dot, that is equal to K into A by L into change in temperature, that is equal to T high temperature minus T low temperature. So as you see that bar is like this and it is subdivided into this. Okay, but the total, if you talk about K equivalent, so K equivalent just now we have found 91.6 watt per Kelvin. So if K equivalent is your 91.6 watt per Kelvin. So how you will do this? So just put the value here because we are taking overall. So overall, if we talk about overall length, so it is your 2L, and area will remain same. Area will remain same. So from previously values, 91.6 into area is how much? So area of the cross section is how much? 0.02. So 0.02 into T high minus T lower. T high is how much? 373 Kelvin, and T lower temperature is how much? 273 Kelvin. So finally we can subtract this 73 minus 273 divided by length. Length is how much? 2 into length. What is the value of length? L. L's value is 0.1. So this is 0.1. So finally we need to find we need to calculate this. If we will calculate this, then we will able to find out that 9916.2 or 1 joule per second. So this is the final answer. In this way we will able to do this. Thank you everyone.